Right, here we are for our review for the Chapter 12-13 exam. And we've got four different problems. Should be able to print these off of Canvas. And essentially, we've got one of the three different coordinate systems, right? Plus some bonus stuff. Like we've got the pulleys, we've got the relative motion. That was the other bonus topic that we threw in there. But we've got an NT system, we've got an R theta system, and we've got a uh, something that could be rectangular coordinates X, Y, Z. And so with that, we're going to be going through doing essentially a chapter 13 problem for each of the three coordinate systems. And that'll, test chapter 12 as well. And then throw in the relative motion and the pulleys, and we'll have everything that we've covered so far. So that's pretty much what you can expect. One of each of the three coordinate systems where you're using force equals mass times acceleration. So let's try out this first one where we've got a block B pulling up on block A. We know their masses, and it wants us to find um, let's see, the required mass. Actually, we don't know their masses. We know the mass of block B. We want to know the mass of block A so that when we release it from rest, block B moves 0.75 meters up in 2 seconds at a constant acceleration. All right. So, well, I guess we need to relate how these things are moving relative to each other, right? We also need to come up with what is that constant acceleration, right? So there's a couple different ways we can come at it. If we wanted to do first our, uh, here, let's see if we can split screen this like so. There we go. So if we were to come up with our relationship between block A and block B, I think that's going to be a nice thing to know, right? So if we look at the statics over here, we've got three chords pulling there. So that would be 3P there, right? If this is all one chord, we'd have 3P pulling up there, 1P there, right? That's P, 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 P. So yeah, it looks like as we move this, um, this is going to be moving 3 times as slow as that guy, right? So that was our mechanical advantage. But essentially, what we're coming up with is the acceleration is what we want, right? We don't care about the velocity as much this time. The acceleration of A is 1/3 the acceleration of B. And we just did that by saying, yeah, it's the same relationship as the mechanical advantage, right? If this was 3P pulling up, then that's 3P pulling down. So we've got 1/3 the weight here as we need there for equilibrium anyways, right? It's not going to be exactly 1/3 because we've got, well, we don't have friction, but we do have acceleration, right? That's going to require more force to accelerate more. Okay, so we've got that relationship, excuse me, starting early today. Um, we know the acceleration of B is constant. Okay, to go in 2 seconds. So I guess we don't know what that is yet. Um, all right. So let's see if we can come up with a constant acceleration for either one. Okay. How about let's start with finding AB. If AB is also going to be constantly moving 0.75 meters in 2 seconds, then we can think to ourselves, all right, what's a good equation that I could use to find that? Constant acceleration equations. We could look and find this one, right? plus V naught T plus 1/2 AT squared. If that's the one we need, well, then let's go to a final position of 0.75 meters, starting from zero, starting from rest for our V naught, and that could be 1/2 whatever A B is, T squared, and they gave us T 0.2 seconds, so 0.2 seconds squared, and with that we can solve for AB. So AB would come out to 0.375 meters per second squared. So far, so good. Then AA has to be 1/3 of that. So that is going to come out to be 0.125, 1/8 of a meter per second squared versus 1/3. Okay, so far, so good. We've got this constant acceleration for A, and they wanted us to find the mass of A. So now we get to do our good old chapter 13 stuff, right? This is kind of the chapter 12, constant acceleration, pull out the right equations, use our pulley idea. Now we'll do the chapter 13, which is say sum of the forces equals mass times acceleration. So if we do that, we need to come up with a free body diagram for both of them, right? Or at least for A. Trying to think what's going to be the most useful one here. Probably A if we want to solve for the mass of A, right? So let's look at A. A has the box. It's got its weight, which is some unknown mass, times 9.81 meters per second squared. It's got the tension, whatever that P is. Any other loads there? No, that's it, right? Although, if we make that P, we better make this actually 3P. That way, I think we're going to still need to go to block B and solve for what P is, because, right, out of here, we could say that equals MA, where it's accelerating upward, right? Mass times acceleration. We still have two unknowns. We don't know the mass. We do know A, B, or AA, but we don't know what P is. So we got to go to the other one. All right, let's make another free body diagram. Let's make one for the block B going up the ramp, something like that. It's got a tension force on it, P, no friction, does have a normal force. And it does have an acceleration, but that will go on the other one. The mass times gravity would be 5 kilograms times 9.81 meters per second squared. So there's its weight. That's all the forces on that one. Equals, let's make a similar diagram, but mass times acceleration. There's its center of mass, and it is sliding up the ramp with mass times acceleration B. Yeah, and we do know that mass, so that's good. Because now we can come and do this one. You could say the sum of the forces in the, if we want to call that the positive x direction. I'm going to move my P there so I can draw my axes. That's going to be my x direction. This could be my y direction. And if I sum the forces into x, I've got equal to MAB. In the x, I've got positive P, and I've got a negative 5 kilograms times gravity cosine of whatever that angle is. So we need that angle. And that angle has got to be the opposite of 60, right? Because this right here is 60. So if that's 60 there, then this would be the 30, right? So we could have cosine 30 there, because this would be 60 right there, right? Or you could do sine of 60. So we've got cosine 30 there. And anything else in the x direction? Oh, we just got the normal force. It's not involved. Equals mass of B, which we could plug in 5 kilograms times AB, which was the 0.375. Ooh, getting real short on space there. 375. Plug that in, and we've got one unknown out of there, so that's great. We can solve for P is 44.35 newtons. Now, that's not an answer, but we did need that to come back to here, right? So if we use this diagram, oh, smeared stuff, we've got the sum of the forces in the y now equals MAA. So summing the forces, we've got 3p going up. So I'm going to plug in the 44.35 newtons that we just solved for, minus the mass of A times gravity. May not have enough space here. Equals, I'll just go like this, MA unknown times the acceleration of A, which we calculated earlier. Or that one, yeah, that was what we got from our relationship between block A and B. 0.125 meters per second squared. Now we've got one unknown, just the mass A, which should come out to be 13.7 kilograms. That's our answer for that one. So looking back through it, all right, we needed to come up with the acceleration of A, and so we used our constant acceleration to find the acceleration of B, and then we used our pulley relationship to make that the acceleration of A, and then the rest was just finding our relationship, or not our relationship, but our force equals mass times acceleration, our two diagrams, and summing the forces to find that unknown. And that is it for that one.